data junkies, welcome back. We are in the home stretch. We are in topic 9.8 on power as it pertains to the two-sample hypothesis testing for Z and T tests with your host, Shawn Janzen. Again, I'm coming around with a little bit of hoarseness, so please forgive me on the video. I'll see if I can redo this video later once my voice comes back a bit stronger. But as we enter into this last video, I just want to kind of recap. This is coming back from just recently watching videos for effect size, non-parametric tests, proportion tests, and things like that as we wrap up the two-sample hypothesis testing for Z's and T's. So let's just do a quick recap on what is power. Power is the probability of correctly rejecting the null when it is false. Okay, think of it as this is a number that's going to help you figure out, am I doing the right thing when I get a number right? Am I rejecting when I'm supposed to? Am I not rejecting when I'm not supposed to? So ideally, power is going to be measured as a statistic, and you want that statistic to be around 0.8 or 80%, which means that if you get a statistic, you're going to be 80% right. You're going to be right 80% of the time to reject the null when it is false. Right? And so that's where you want to be. Of course, higher power is always better, so 80 and 80% is just your minimum. Now, when we're talking about power, we're going to be talking about curves a lot in this particular video. So let's start with the null curve. Is this the only curve that we're thinking about? In a previous video when we were talking about effect sizes, I said no, it's not. And what we have on the screen here is just sort of a null distribution curve, and centered at the middle is a 0. And at 0 is the difference between your two variables, group 1, group 2, and they have a mean, you subtract them, and we're saying that with the null hypothesis that difference is 0. So that's in the middle. And then we go out towards the tails. And if there is differences between these two groups, and if that difference is going to be large enough that it is going to be unlikely to be true, then we should see those out in the tails, and that's going to provide sufficient evidence that we can go ahead and reject the null hypothesis. If it doesn't make it far enough out into the tails, if it's inside our goalposts toward the center, then we're going to not be able to reject the null hypothesis. We're going to fail to reject it. So let's go ahead and see what we can think about then. I mentioned before that the null distribution curve is not the only curve around. There could be another curve, and this is our alternative curve. We're saying, you know what, the difference between these two groups is not 0. It's actually -3, or +9, or +82. What we're saying is it is some value centered other than at 0. And so we're going to be able to draw a distribution there. If we had multiple hypotheses, we might actually have multiple hypothesis curves. But in this case, and what we're dealing with right now, we have just the one alternative to the one null. And so what we can see here are there two competing overlapping distributions. The dotted lines that you see here, those are the markers, the goalposts, if you will, for the critical values on the null distribution. Those are the areas that we have to get past to get into the tail, to consider ourselves to be statistically significant and reject the null. The green distribution here, we are trying to make a case that says the difference between our two groups is -3. And so our alternative distribution here is centered at -3, which is just to the right of that goalpost there. So if we were to take that at face value, we would say that value is not into the tail far enough, so we can't reject the null hypothesis. That's not how this works. That's not how this works at all. What we're looking at is saying, with this alternative distribution curve, there's a chance we could get values anywhere inside that alternative distribution curve. And that includes some values that are going to be far enough out into the tail of the null distribution. The farther apart our alternative and null curves are, the more likely it is that we're going to get a result in the alternative curve if the null is false. Keep these things in mind. So go ahead and take a look at this then. I just mentioned that we could have the probability of the z-score and calculate where that's at for a critical value of 5 when the alternative is at -3. And I can go ahead and see what is the chance of detecting the alternative. That's what we're really looking at with these power tests. If there is an alternative distribution out there, what's the chance I'm going to be pegging it? I'm going to find it. So we're starting with a z-score, and we're just doing a classic x minus mu over standard deviation, where in this case, x is the goalkeeper post that we needed to get past, right? In that case, in the null distribution, the post we needed to get past was -3.32, and mu is going to be the value from our alternative distribution where we think the population mean should be, and that's -3, and that distribution had a standard deviation of 1.7. If we take those values and we plug them into a z formula here, it's going to give us a z-score of negative 0.188, and if I take that z-score of negative 0.188, plug that into a p-norm function, it's going to give me the probability of getting that particular z-score. And that probability is going to be 0.425, or about 42.5%. So if I was to go back and revisit this graphically, I have my two curves, my null and my distribution, and 42.5% of the alternative distributions curve is filled up. I have about a 42.5% chance of getting a score inside that green shaded area if the null alternative is false. Now, some of those probability scores are going to be included in the tail of the null distribution, sufficiently enough that I would be able to reject the null hypothesis. So how can we go ahead and figure this out? Let's go ahead and take an example here and see how we can break it out. Let's start with asking ourselves, when is it that we can reject the null? So YouTube is testing a new algorithm to place video advertisements that is based on the length of the video. Previous knowledge shows that 2 minutes and 45 seconds is the average watch time before the first video advertisement is tolerated by the users, with a standard deviation of 42 seconds. A new algorithm tested on 100 videos finds that the new tolerated average watch time till the first advertisement is 2 minutes and 38 seconds. Now keep in mind, these are different people watching these on different videos, so this isn't the same sort of groups. These are different groups, and we're just looking at how this differs across the two different types of variables. So why is a question like this important, and why would we be doing power analysis on this? Well, first of all, implications show that too many ads and our YouTube viewers might stop watching those videos. And this could also get angry video content creators that are having advertisements put on their platforms, etc. In addition, if there are too few ads, then YouTube is going to have a lower revenue stream, and it's going to have to find other ways of making its operations work in the red and profitable for Google. So if I was going to go ahead and put this into hypothesis terms, my null would say that the mu is 165 seconds, which is the 2 minutes and 45 seconds converted. So that's going to say that the ideal time for advertisement placement is where it currently is at 155 seconds. And that the alternative is going to say, well, it's going to be something other than. We're not really concerned yet at the moment if we should be going higher or lower, but just not 165 seconds. And we're using a small alpha this time, even though it's only a sample size of 100. We're using a small alpha this time of 0.01 because the boss says that this is really important. It's more important that we don't commit a type 1 error right now, so we're being authorized to go with a lower level alpha. And so we're going to ask two questions from here. At what x bar, at what mean, do we need in order to start rejecting the null? And then also, what is the power if the true new mean is actually equal to 2 minutes and 38 seconds? That was the time from our 100 videos. So let's go ahead and start with what we're given. N is 100 for videos. Sigma, the standard deviation of the previously known video content, is 42, with a mu of 165 seconds. We're given an x bar of 158, but we're not going to need that just yet. And we have an alpha of 0.01. So what I want to start doing is figuring out what z is going to be. Alpha is two-tailed, which means I'm going to split my tails into 0.005, which is going to correspond to a z-score of 2.58. So far, so good. Now I go ahead and start looking at what is the probability of getting a particular z-score that's going to be satisfying that level of z. So we're asking ourselves, if you're looking in formula notation, what's the probability of getting a large z greater than small z, where large z is talking about some population score, and small z is talking about the critical value that we have, where it's smaller than our alpha of 0.01. And in this case, I'm looking up to see what is the probability we're going to get a z-score greater than 2.58 or negative 2.58. It's plus or minus. So we go ahead and take that, plug that back into the t-test formula. This is looking at the one sample version here, but it is easily adapted for the two. And I'm looking at to see how we can go ahead and take this formula and rearrange it so we can get x bar by itself on the other side of the inequality operator. So we have x bar is greater than mu plus or minus z times standard error, where standard error is defined as standard deviation divided by square root of n. And if I take the value numbers I have, I plug them in, and what I come up with is that x bar is either going to be over 176 seconds or under 154 seconds, and they're rounded. I rounded these to whole integer numbers because for the most part we're just counting seconds as whole numbers here in this case. We're not counting partial seconds for commercial airtime and things like that. So we just sort of walk through this. I want you to look at this for a moment, though, and see, how did we manipulate and rearrange the formula? We plugged in the numbers that we had, and how did we go ahead and compute across? And why did we have two x bars? Remember, this is two-tailed. So we could potentially reject the null if we're getting values on either side. But what we're about to see is that the probability of getting each of these values is vastly different. So another way I want you just to be able to think about this is sort of a rough eyeball test. It's not super scientific and approximate, as we're about to see. But what you could do is say, all right, if my alpha is 0.01, that could correspond to a 99% confidence interval, roughly. And that could be approximated within plus or minus 3 standard deviations. So what I did was I went ahead and took the 4.2 standard deviations and multiplied them across by 1, 2, or 3 standard deviations, and that built me out how far they are. And so I could just take 3 standard deviations plus and minus off of the average there, and that's going to help figure out that my range for my confidence interval would be about between 152 and 178. Now this is really close to what we had before. It's the exact same value of 152. The high-end value is a couple numbers off, could be due to rounding and other particular differences there. So when we're asking ourselves what x bars will allow us to reject the null, what we would conclude is that videos of less than 154 seconds or greater than 176 seconds are sufficient to reject the null hypothesis when alpha is 0.01. So let's move on to the next question of what is the power if the new mean is 2 minutes and 38 seconds? Well, here we need to start up again and work our way through. So we have an alpha of 0.01, and I already know that my range of possible x values is going to be somewhere between 154 seconds and 176 seconds, so to speak. And I can go ahead and calculate this out into a left tail analysis by plugging in the time I had on the lower end minus what we believe to be the population mean at that point, which is 158, divided by our standard deviation of 4.2, and that's going to generate for me a z-score of negative 0.913, which when I go ahead and put into a p-value is going to tell us that we have about an 18% chance of getting into that tail. If I look at the right tail, I have the much larger number. In this case, it's over 175,000, and we're subtracting that by 158, dividing that by our standard deviation of 4.2, which is going to give us a z-score of 4.247. Now this is a very sizable z-score, so let's go ahead and find its p-value. And the p-value associated with such a large z-score is going to be very small. And in this case, it's 0.999999, and I stopped typing the 9s, but what that's going to come out with then is that we're going to have a p-value. The chance of getting this z-score so large is very small. It's about 1 with 5 or 6 zeros after it. It's ridiculously small. So let's go ahead and see how this is going to look graphically speaking. So I've gone and plotted out for you a null curve in green and an alternative curve in purple. And in the green curve, I've colored in the tails down on the bottom with a sort of red color so we can see, are we going to get scores in that area? Now the purple curve, it's continuous, it's going to keep going, and it's going to have overlap with the green curve in some of its parts. So the parts on the left, that's where we have our right tail power, and this is where we are going to pick up our 0.18% probability chance. So we're going to have a greater chance of finding a video time score that is less than the current mean of 165. Whereas on the other tail, the curve goes down and it keeps going out to infinity with all of the other normal curves that we're plotting. And here it's plotting out and says you could get to reject the null if on the right if you're getting values larger than about 178, which is going to be 177, which is going to be approximately the very small probability chance of this actually happening. Could it? Yes. Probably very unlikely. So the way we can read this is that if the true mean is changed, given alpha 0.01, we will only detect it about 18% of the time. I'm not even going to include the other tail at the moment because it's so small. We would sum these together to find the total chance of detection. So at this point, I'm really just looking at the probability of the one table area that we have. And we only have a power of 18%, or 0.18, which is pretty abysmal. So let's ask ourselves then, how big of an N do we need? If power analysis is driven in part by sample size, and we've already got some other things fixed at the moment, how many more people do we need? So alarmed with the previous findings, the YouTube research team plans to collect another sample. The power was too low last time, it was 18%. So what sample size would they need to obtain an 85% or 0.85 power? The teams plan to generate a sample with the same deviation of 25, alpha of 0.01, and it's also going to have an unstandardized effect size of negative 11 seconds. This is derived from the benchmark where we found a potential mean at 154 and detected an alternative mean with it. That was 11 seconds. And in order to do this, we're going to need the power.norm.test, pwr.norm.test. And in order to get that running, we're going to need the d-score. Now the d-score I said above was 11 seconds, but that was unstandardized. If you're going to use the function in R, it has to be the standardized version, the Cohen's d. So in this case, we need to use one of the Cohen's d functions or formulas. In this case, I'm using the formula. It's quick and easy. And I'm generating a d-score of 0.262. Once I have that, I have all the values I need to plug into the norm test. So I'm going to leave n as null. I want to know the sample size. Sig level at 0.01. Power at 0.085. That was our minimum standard. And an effect size of 0.26. When I go ahead and run all that through, R is going to tell me that I need at least 193 people. And this is 193 people in every group. Keep that in mind. With this particular test here, we only had the one group and we were comparing it to preset data. But if this was an exercise that had two groups, then we would need to go ahead and have 193 in each group. And that's how we go ahead and read these. And if we were to plot this out with a power plot, we can see here where our curve was left off. I left this in case here to where we can see our 193 at 80%, and we could see how we were dropping off at lower values, such as 10. Moving on, the YouTube research group is back once again and they're asking for our help, but this time they want to see if two different focus groups of 14 people each react negatively to a new advertisement placement compared to an earlier trial version. And they want to know, first of all, what kind of Z or T test should they be conducting on this data? Go ahead and pause the video for a moment while you think about that. The answer is that it would be an independent two-sample t-test. These are two separate focus groups with different people in each one, and they're looking at this data together and they're getting a comparison. And the researchers here are using what we call a thermometer scale. Thermometer scales are typically coded from 1 to 100 or 0 to 100, where just like a thermometer, a high number means hot and a low number means cold. And it's usually some sort of sentiment rating here, where if you're feeling cold towards something, you don't like it, you hate it, you're disagreeable to it, negative associations. And whereas high numbers, you like it, you love it, you want more of it, and they are positive sentiment association numbers. So these YouTube researchers, they're using a thermometer scale, which we can treat as interval or ratio if we want to shortcut it. And so we should be good with the dependent variable. But it says that the first group had a score of 73 and the second group had a score of 57 with standard deviations of 13 and 19 respectively. Using an alpha of 0.05, are these differences statistically significant? Now, what I should be doing is a variance test first, but I just have point estimates, so I'm going to go straight into calculating a t-score. And in this case, the t-score is going to have a 16 on top when we subtract the two differences. I'm going to pool results across the bottom into getting 6.153, which is going to give me a t-ratio, a t-statistic of 2.6. 2.6 is my ratio of the mean difference to the standard error. And I'm going to have degrees of freedom of about 26. That's n plus 1 plus n of 2, both of 14, minus 2. And these values together, with my degrees of freedom and the alpha I was already given, I can find out that my t-critical value is 1.71. 1.71. And so if I go ahead and compare my t-statistic obtained to my t-critical value, t2.6 is much larger than 1.71, and so yes, we are certainly statistically significant. But then the researchers come back and ask, well, what about the standardized and unstandardized effect sizes? There's differences there. Tell us about it. So in this case, the unstandardized difference on the thermometer scale is 16 points. How did we know that? Well, we were given that the one group had a score of 73 and the other one had a score of 57, and all I did was subtract the two. And this is quite large on an unstandardized presence, because if we consider that a thermometer scale is only perhaps 100 data points, possibly, then 16% of those are being used up by people on these potential differences of opinion here. Some are much higher, some are much lower. 16 percentage points. I think that's substantial enough. You may have your own separate opinions, and I welcome a discussion about them. Now, the standardized version is where we're going to introduce Cohen's d here, and it's going to alter just a little bit. So in this case, I'm going to take the easier formula of the 2 times t divided by square root of n, because I've already solved for t. So I plug in 2.6 up in the numerator, standard deviation and whatnot in the denominator. Sorry, n in the denominator. And that's going to produce for us, when we work itself out, a d-score of 0.98, which on our french fry size scale is also quite large. So that kind of helps balance out a little bit when I said that our thermometer scale was 16 percentage points and the d-score was 0.98, which is also large. So then they ask us, well, what about the power of the test? What is the power of the focus groups test here? So for that, we need to go into our power analysis. We're going to grab the power.t.test function, and this is going to be a little bit different than the power.norm. We're still going to say that we're going to null on power because we need to know that. N is 14. 14, why not 28? There's 28 people. Oh, but they're different groups. And what you need to do is put in the n that represents the equal size groups in each group. Sig level of 0.05. It's a 2-sample test, and it's a 2-sided, so it's 2-tailed, 2-sample. These are different. And I'm putting in my effect size of 0.98. When I go ahead and run this, it tells me I have a power of 0.704 and rounding, and the YouTube guys are going to be sad because that's not 0.8. It's not far under 0.8, but it's far enough that they need to be concerned about it. So is the power level acceptable? Produce a power plot to reveal the size that we should be using. So go ahead and take a moment to see if you can figure out how to do that, and come back. Alright, so when you're back, all you needed to do was take that power analysis we just ran, save it into an object, whatever you want to call that object. I think I called mine power plot, and then run a plot on that object, and it will produce for you a plot type device here. So if we want, we could go up and look at 80 and cross-reference that over, and we're going to find it kicks in somewhere at about approximately 18 people. We would need an exact number to be sure, but it looks like it at about 18 people is where we're going to hit that 80% threshold. So they just need to go get a few more people into each group next time they want to do a focus group to help get there. Now, I want to leave you off here with 4 different ways that power can affect, 4 things we can do that affect power to help reduce type 1 errors. So the first 2 are intrinsically related. They have the same effect. 2 different things, but they're going to have the same overall effect. First of all, increase your sample size. Keep in mind we're using this standard error when we're dealing with this, and the square root of n is in the denominator. So when you increase your sample size, you're increasing your denominator, which makes the overall standard error smaller. Same thing happens with standard deviation. When we decrease standard deviation, that one's in the numerator, it is also going to help generate a smaller standard error and a smaller margin of error, etc. So keep in mind, visually speaking, when we work on this, when you're decreasing the standard error, it is causing our distributions to become thinner and tighter and taller. So it is reducing the amount of overlap between our distributions when we do either or both of these strategies. Another approach we could do is increase our alpha level. If you want to reduce a type 1 error, keep in mind, the type 1 error is when you reject the null when you're not supposed to. So if you want to make sure you're doing it right, increase your alpha. Increase the size of that critical region under the tail. And so that's exactly what it does. It's inversely proportional to the type 2 error. As you increase type 1, you are decreasing type 2, and vice versa. Visually speaking, these 2 curves could overlap with each other, and when alpha is smaller, there's less area being shared between the null and the alternative. When you are increasing alpha, assuming there's nothing else to move the distributions, you're just increasing alpha, that is increasing the area shared by both curves. That will hopefully allow you to get a value inside the alternative. We see it in the null, but it's also in the alternative, or at least it should be if we're getting flagged for significance. The last one I want to tell you about is get yourself a larger effect size. Predicting larger effect sizes, or just plugging in ones that you may have come across, are a great way to figure out more sorts of range type issues. It widens the gap between the mu and the alternative, the null and the alternative distributions. And if the gap is large enough, then these distributions will barely even overlap. So whenever we go out and run a test and we get a particular statistic, it's just going to go ahead and already flag it as being significant or not because the effect sizes could potentially be so large. However, this is a very arbitrary approach. This requires you to either have data already that has these sorts of effect sizes that you can manipulate to see what it looks like when it's larger or smaller. Most of us don't have that. So what you could also then do is manipulate other data sources to see how it works out, or go ahead and intentionally collect data to get representativeness on across a variety of scales, so we don't have to worry about a lot of these particular issues here. But on that, I just want to go ahead and wrap this up. This is going to conclude our section on Z and T, two-sample hypothesis testing. It's been swell hanging out with you guys online. I'll see you all in the next module where we start talking about ANOVAs.